we're gonna do topology optimization by using the same structure, namely FEniCS. So in order to do so, we are going to design the direct problem, of course, in FreeCAD. So I have started a new document, so we can try to do something maybe in the part design. So let me try to do something like a bracket I have in mind. Okay, so let's try to use, for example, this one, and then I can use also like these multi-lines, so in order to make a little bit like a quicker version. So if you think that I'm doing now by using the Control M, right, once, and Control M again, and Control M the third time, so you see I can change between how I can, instead of using like lines, now I can do a curved structure, and now it has changed automatically by giving me an tangential extension here, which is really nice. So then I can try to close it here. Of course it will be difficult to close, so I can do it from the other way around. So that means I can now use this one. Now I can use Control M, one more, and again, and it changes to this curved structure, and we'll try to make it symmetric. It will not be symmetric, definitely not, but I can try to do it. So by the way, it didn't snap in, right? So it is not really correct. So I'm using escape and then try to delete that one by using delete, and now I can use a normal, just one line, so I can try to make it better. Oh yeah, okay, now it snapped. So now I can try to not rotate, but just want to distribute. So by the way, if you just get out of this, like the as you wanted to see, so you can always click on the stop, so it comes back. Now I want to use like fixation in such a way that, for example, I'm going to put the constraints so that dot will be here. So it's like 2 degrees of freedom less. Oh, I don't want to do it now. Let me undo. Let me try first to give these directions, maybe like this dimension of that one. I don't know, maybe 70. Because I don't care, technically speaking, a lot about the dimensioning itself, but I want to have some sort of dimensioning in order to make it symmetric. Okay, so like let's 25 for example, and here I need to use also 25 here as well. Okay, now it looks like symmetric. Of course I need more, like 6 degrees of freedom more, in order to close or make the sketch unique. And for this one I can maybe try to have this distance. Oh, that's not correct, so maybe I should have the distance from here until that point. I don't know, 40. So now it looks like symmetric, and it is also nearly closed. So I think I also need to have try to bring it to one position. Okay, it was not running well, so I will go back and ask why it is happening, because this is like free to move, right? So I need to fix this distance as well. So I'm trying to fix this distance. So I don't know, maybe 27, and I need to say that the same kind of stuff is here as well, so that it's fully symmetric. Now I have 3 degrees of freedom. There's still something missing. Oh, maybe the curvature, right? So I can try to have a look if this is something with the curvature. Yes, I need to give this curvature. Let's put it 18, and oh, I don't like it because there's already like too many constraints here, so I cannot use it. Saying, and oh, this is something else. Let's try to, okay, let's try to resolve the issue that I'm trying to delete some of these stuff, right? So I'm going to delete that one, and let's try again, because I really want to have a symmetric stuff. So let's try again. Okay, now I can use 18. Why not to use here 18 as well? Now I have only 2 degrees of freedom. That's exactly the stuff that I can position it anywhere, but it is fixed, so it is not changing if I try to drag and drop somewhere else. So this is why I'm using here a constraint which is saying that this dot is fixed here. Okay, now it's fully constrained, it's green. I can leave it, and now I can try to do a path. In most of the cases, it also works if you don't fully constrain it. But if you want to do a more complicated stuff, it is better to do it because then you have more access with the subsequent stuff if you want to build another part and so on it. But this is what I want to have. I want to do some holes on it. So this is why I'm selecting this face. And after selecting the face, I can go to task and say create a sketch, and it will automatically create the sketch on this plane. So I want to use now here and something. I mean, I can of course try to fix the position. Let me fix the position here, and now it is handy to use it this dot. Okay, so I'm going to give some dimensions here. I can also use this dimension, and let us do non-symmetric in such a way. And also I need to say this distance from that point until that point is given. And now I need to have one more like this distance, then it will be fully constrained. So I'm not trying to do it symmetric on purpose. I'm not doing it symmetric. And oh, there are still 2 degrees of freedom. Oh, of course, the diameter of these circles I forgot about them. So let's make a small one. Why not to have a little bit of a larger one? Now it's fully constrained. It's always good to have fully constrained if you have problems with hole and so on. It helps if you have fully constrained. So now we have that. By the way, so it is saying that the diameter is 6. So this is technically not, oh, this is not really what I want. So I don't want to have them. So let me go to the sketch and say you want to have a pocket. Then I will have also the correct sketch chosen, and this pocket needs to be going through. So why not to make it through? So if I do it large enough, then it will go through. Okay, so I can of course try to make it a bit more fancy. So let's try to use that one, something like holding on it. So I'm going to create a sketch here, which is again not so important to dimensions. Maybe let's try to do something like that. And now I can try to extrude it in the other direction. So let's make it a bit larger. What I have in mind is like I'm gonna hold it and bring some forces here, something like that. This is what why I need that. Okay, it's more or less, that's a really fancy kind of a bracket, and I can now live with that. Let's go to FEM, and again for the direct problem in FEniCS, what we need to do is the mesh, only the mesh. We don't need anything more, so I'm not doing any analysis. Instead of that, I'm just clicking on the Gmesh, and now I'm giving it like simply a coarse one. Of course, I can try to make it a little bit like a finer one. So maybe this is finer, yeah, just a bit. I can try to make it maybe 2. This looks okay. And now I need to be able to find out later on in FEniCS where to bring the loading and where to have the clamping and so on. This is why we have used the mesh group. So after selecting the mesh, if I say mesh group, then I can, first of all, I need to choose label. This is what we are going to use. And now I can say add the body, and then even I can open it and I give a better name. So this is good because later on we are going to use these names. So I'm giving the name body. You can just give whatever you like. So then I'm choosing again the mesh and saying from the mesh group, again using the label, that's important, and a face in order to be able to bring the loading. For example, I can say this one and maybe even this one. So first add and then. So these 2 surfaces I'm going to use for something. For example, I can use them for clamping, right? I'm gonna say clamp. And then last but not least, I need a force, right? So I'm going to use this surface in order to bring a force on it. So that means this is where I'm doing the loading. Alright, now it is grayed out as you see here because these all labeling is not incorporated in the Gmesh. So I want to do an apply, and what it does is, okay, doing the remeshing. but also putting the labels in the correct position. Now we're done. So after choosing the mesh, because the mesh groups are inside, right? After choosing the mesh, I need to export this mesh in order to be able to import it later on in FEniCS. So I'm going to create a new directory, which is on the desktop Freecad path. You can just have whatever you want. I'm going to put like topology optimization 4. And important thing is that I'm searching here from FEM mesh for FEniCS. That's the important part. So XML is not something that we're using. We are using XDMF. I can give the name whatever I like, but ending has to be XDMF. It is allowed to have one of them, and they are different. They are of different structure. So I need to use XDMF because for importing we are using that. If I put it in topology optimization 4, it's asking me like not mark and mark. So I can put whatever number I want to have here, but this is important to know what we put. I just leave it like 1. So that means if a surface has the marking 1, or if the surface, like for example clamp, is one of these surfaces, I can zoom in. So if this is the surface, a triangle, here it has the mark 1, but if I have a look on this triangle, it has the mark 0. So then FEniCS can find out where to integrate the forces that we bring in, or the Dirichlet boundary condition for clamping that we bring in. If I say OK, then it writes out. Now I can open the optimization code. So that's the optimization code. We will talk about that in the lecture, and then you will also find it, and of course like in the cloud. So here's the Freecad version. That means I'm first importing the part, right? So this is topology optimization 4. That's the directory what I have, and inside I have a file which is called part.xdmf, and from this part.xdmf I'm reading different stuff. First of all, I'm reading whatever it's labeled body, which are the 3-dimensional cells. So I'm also reading whether it's written loading and whether it's written clamp, and create different lists. For example, there's a list with loading list. That means all the surface elements 0, 0, 0, 0, and once a while it's a 1 if it's on the surface which we have selected for loading. So the rest is more or less similar that we have. This is like the volume fraction. This is the penalty factor for the SIMP method that we use. And I'm also using here the Helmholtz filter, which this is necessary for the Helmholtz filter. And I want to write it out, of course. I'm writing out as an XDMF file, and also I'm writing out as a PVD file. So there are no huge differences between them. XDMF is like writing every time into that, so it's difficult to open when iterations are not done. And PVD is like trying to do for each iteration a new file. So it may be more handy, but then you will have a bunch of files, right? So it is a little bit of a taste, whatever you like to use. So for large problems, XDMF may be nicer to have it, but technically speaking, for a small problem like that, PVD is perfectly fine. So then we have, of course, material numbers like the Young's moduli and the Poisson ratio. What I have in mind is a bracket out of kind of a peak plastic. So it's a plastic, which is a hard plastic around 2 gigapascal, and the Poisson ratio is more or less like 0.4. This is why I have chosen like this. Of course, if you use another material, then you need to adjust this here. And then what we do is now here using the subdomain data loading list. That means have a look in the loading list. Whatever there is a ID 1, which is marked, right? Marked as was 1 in Freecad. Whatever there is an ID 1, then put it into DA, because I'm going to use this DA in order to take the integral over the elements which have the ID number 1. So that's the whole idea. If I write in the Freecad something else than 1 for the mark 1, 8, 11, whatever you want, then you need to change it here as well. So now we are creating the spaces, and we are creating also the space for the Helmholtz filter. So this is why we have once a solution and once another solution for the Helmholtz filter. So now here you see for the first time maybe one of the benefits that we use here FEniCS. So you can have a look here. There are like possibilities to tune the solver parameters. So I'm using here a solver which is an iterative solver, which is a really powerful one and a way quicker one than a direct solver that we normally use. For example, if you do this in FreeCAD, then you can really use here some solvers which are state of the art and way quicker. I mean, technically speaking, they are the quickest in the world. So any commercial program, they cannot come near to the speed of these solvers, but using the solver is just another science. So mathematicians, they know, but they don't tell us. So as a poor engineer, what we do normally is like we don't know which solver is the best. We simply try, okay? We simply try and find out which one is the quickest and which one is also converging. So you may have numerical problems if you use one of these iterative solvers. You can try another one and find out which is working. So I'm using here something which is BCG. CG is conjugate gradient, and B is like B conjugate gradient stabilized. So it's a name of that. So of course you don't know why the name stands for. There's a mathematical description which is based on conjugate gradient, which is good for stiffness problems. So that means this is supposed to be working fine. So let's have a look. And I'm even making it quicker by using a preconditioner. So in a similar setting for the Helmholtz filler, I'm using the CG. I don't need the stabilization because of that I'm using CG with a preconditioner incomplete lower upper decomposition. So again, it is simply stated and honest with you, trying and finding out which one is working best. So now we have the loop here. This is more or less always the same loop, that we have solution first of the stiffness problem, and then we find out the sensitivity and use the sensitivity in order to find out which one to drop and which one to keep, then solving a filter in order to make it more smooth, and then later on in order to get something written here, I also use a print here. So let me try to open it on the terminal, and I don't know why I cannot run it, but let's try to do so. Okay, so my terminal is not allowing me to use a tab. It's weird. Okay, now I got it starting and now it's solving. So you see there's like a change, and this change is getting smaller and smaller. Technically the while loop is doing, unless either we get like 2000 iterations, then say okay, I cannot do it more, or if the change is small. This change is calculated here by using the normalized mass density, new and old one, and the difference and the integral over that. So that means if this is really nearly zero, that means in each iteration the change of density is so small I don't need to solve it anymore. How small this number has to be, no idea. Again, you need to find out by just changing and trying to see. And now it is roughly finished, so I can now have a look in the paraview. So I have two different types of solutions. One is the PVD, so I can open the PVD, or another one is the XDMF. Okay, so there's no huge difference between them. So I'm going to open the PVD and then try to see how it looks like. So we have 42 iterations, and I can go to the beginning, try to do it like a little bit slanted so it's easier to see and see what it's doing. So no shocking news. So because we are acting like forces here on this one, so the algorithm is suggesting to keep whatever red is to keep, and whatever blue is you can get rid of it. Of course you may have design problems, right? You can say no, I'm going to have a pin here, I want to have it closed in order not to get away, right? So you can say I will still keep this one just because of the design restrictions that you may have, but definitely speaking you don't need that one. But it's interesting. Maybe I would immediately say just cut the hole, but it's not actually. It's also keeping some of that. It's not getting the hole away. Probably there is something difficult to see, kind of a moment here which is exploding, and then this moment is of course smaller if you keep this distance larger, so it's holding in the middle something. It's hardly impossible to to say it from the gut feeling, but the algorithm is suggesting this. And here is also really interesting. I mean, how you would be ending up of getting rid of this one. So we can try to visualize it even better. No, not slice. I want to use a threshold here in order to visualize what is larger than 0.5. And yeah, see, I mean, inside is just getting a bit whole, and this is good because maybe there's like 10% of mass that we can get rid of. So it's a really reasonable and nice suggestion that we get. And we can ask the question, okay, how is the loading? So I just applied a loading here, which is indeed important if you do it like a realistic stuff to have the loading correct. And you see here I'm applying a loading and the direct problem, where I'm applying it on the DA, and DA is the one that we have selected in the loading list. And on top of that, I'm using here TR1, which is given here, right? So this TR1 is a constant and is acting along X and Y. So let me have a look in X and Y. So this is X and this is Y. So here there are forces which are slanted and acting in a different angle. It's difficult to say the angle. 110 and 100 in X and Y directions. So if you want to have a distribution of force, not a constant force, the whole surface, but instead of you want to have a function which is depending on X and Y or Z. I mean, Z in this example doesn't make sense because if you have a look, I mean, the surface has everywhere the same Z coordinate, right? But X and Y distribution you may have a linear, non-linear, whatever you like distribution, and X and Y, and this is, you can bring it here. You can have a vector, this is a vector, right, with 3 arguments. You can have a vector which each of them are depending on, in a linear or non-linear way, on X or Y. I mean, X is X of 0, Y would be X of 1. So we can immediately bring it by using an expression instead of constant. So there are some benefits. If you just have the full control by using the code, you can make immediately more difficult stuff. And also if you want to use a more sophisticated material equation, which we don't do it here, we just do linear elasticity. But if you want to have hyperelasticity or something like that, then it is also rather simple to put it into the code if you have once the understanding of how it is working. But mostly the biggest part of it, if you have a larger system and if you need a lot of computing power, then the choice of solver will be really beneficial to have a control on that. And of course, in the end, what we want to see is the optimized problem. And for this, you have a possibility to use ParaView and do a nice snapshot. So let me do it here. We can try to go to File and then Save Screenshot, and then you can use it as a PNG image in order to create a nice looking figure out of that.